Welcome everyone to the webinar. This is the E4 Carolina's Digital Technology webinar series. It's the current edition of that series. I think we have a real interesting topic for you, looking at digital technologies at the grid edge. But let me say there are other webinars that E4 also addresses on different topics of technology. So if you're interested in that in the energy sphere, let me suggest you go to E4 Carolina's website and you can see some of the other offerings there. But we're real pleased today to be collaborating with SIA Partners. They're the series host and sponsor for this event and have helped bring this content to us, which I think you'll find very interesting. And with that, I'll turn it over to Shane Williams, who's the Chief Client Officer with SIA Partners.
Hey, everybody. Thank you for joining us today for the E4 Carolina's Technology Series sponsored by SIA Partners. I'm Shane Williams. I'm a Chief Client Officer at SIA Partners and welcome you to our webinar today. I want to hand it over to Sean Jump, who's going to give a quick introduction about SIA Partners. Sean is a Managing Director in our Houston practice and is part of our energy team.
Hey guys, Sean Jump, based in Houston, Texas, Managing Director with SIA Partners. Worked in the energy industry for over 18 years. Worked for 10 years directly in the industry as an engineer, leveraging my background out of Texas A&M. Hopefully nobody holds that against me on the call. But yeah, I worked in the industry for 10 years, building large-scale infrastructure projects. Then I moved into consulting for the last 8 years, mostly focused on emerging technologies. So be robotic process automation, it could be smart meters, quantum annealing, machine learning, and AI. Mostly the areas that I tend to focus on for energy companies. Happy to be here today, and thanks for letting me moderate the discussion today. I'll give a quick background on SIA Partners, and then we'll move forward in the agenda. So SIA Partners has been around for about 23 years. We're headquartered in Paris, France. And really, we started out in the financial services arena, and we've branched out over the last 23 years, not only globally, but across multiple different sectors. We've been in the US now for about 12 years. We're headquartered in New York. We've got satellite offices in a lot of different cities, including North Carolina, which is quite a large office now, and Houston and Denver, and we've got West Coast and East Coast covered as well. But really where we cut our teeth beyond financial services was energy. And energy is still approximately 50% of what SIA Partners does. And so we're focused on smart meters, we're focused on oil and gas communities, we're focused on power utility communities, all the emerging things that are happening in those communities through our engagements with clients, through understanding how COVID has impacted the economy, through understanding how the need to change is omnipresent to serve clients and customers in a new and differentiated way. And so SIA Partners has wrapped that into several offerings across the energy sector. And we've been operating in the energy sector in the US over the last about 12 years. And so quick background on SIA Partners, quick background on myself and Shane, and happy to be here and happy to help moderate. Awesome. So I'll introduce these three speakers. I think we've got two more in the next slide. I won't go into detail behind, when we get to the speaker, I think they can give a short introduction about themselves and their background. But just as an opening to help moderate through, we've got Keith Davis, who's the president of Renewable Energy Integration Group. Gary Ratcliffe, who's the VP of Market Development and Innovation at Hitachi Energy. And we've got Sebastian Gerber also joining us from SIA Partners. He's a managing director and probably one of the world's foremost experts on power utility companies based on his background and experience. As we get to each speaker, we'll open it up to allow them an intro. And then as we get to the panel discussion on the back end, we can get a bit more detailed on background if we need. Let's go to the next slide. Excellent. And then actually, I believe our first presenter today is going to be Ryan Kennedy. He is the CEO of Atom Power, as well as Chris Thomas, who's Director of Operations at Ecoplexus. Excellent. And with that, we will hand it over to Ryan Kennedy, CEO of Atom Power. Ryan, maybe you could just open with a brief intro, and then we can dive into your slides.
Yeah, absolutely. Thanks for the the segue in there. I'm Ryan Kennedy, co-founder and CEO of Atom Power. Extraordinary brief backgrounds, 27 years in power distribution, first as an electrician, then as a professional engineer. In a past life, I designed and built buildings, and now am with Atom Power since 2014. So we could probably go to the next slide. So just the briefing about Atom Power. We're located here in the Charlotte, metro region in Huntersville. So we're the first company in the world, still to this day, or the only one that has commercialized solid state digital circuit breakers. We're 100% vertically integrated in that we design and build everything ourselves, including software. So it's a heavily software-based company as well. Around 56 employees actually today. We added one since this slide was developed. And everything that happens within our company, all products are produced right here in North Carolina. We can go to the next one. So a little bit about what we do is our primary market target, is in electric vehicle infrastructure. So we see EV charging not so much as the EV charger. We see it as a infrastructure problem that has to be addressed. And how we do that is in its shortest form is we charge cars directly from our circuit breaker. Instead of having to build an autonomous unit individually out in the field. And this has many value propositions that I could dive into later for those interested, but nonetheless, just a quick view of what we do. We can go to the next slide. So if you kind of think about, what energy is, you may have to click one more time. Energy is actually pretty simple. You have something that generates it, something that distributes it, and something that consumes it, whereas consumption really is the thing that drives everything related to generation and distribution. So that consumption rate, how often, how long, what's the average, what's the peak, especially the peak, is really, really important. All of that defines everything upstream from the consumption level. Go to the next slide. And so let's take a look at that real quick. If the consumption sort of rules the roost on the grid, then let's look at some quick energy consumption data. I mean, lighting used to be kind of the heavier load on the grid for up until say the 50s, but today you have roughly 2 kilowatts, and this is the average home in the U.S. About 2 kilowatts for lighting. 4 kilowatts for hot water heater, and that's pretty standard actually. It's surprisingly standard in the U.S. At 4 kilowatts. If you have a sizable home, you have an HVAC compressor that's going to be 6 kilowatts. And if you kind of go between the lighting, hot water, and the HVAC and the hot water have typically been the highest loads in the home, But add an EV charger into this mix. And by the way, this is representative not just of the home. I wanted to show the home stuff because it's representative of the same impact on the commercial space. So basically everything else. If you look at EV charging, we're talking up to 19 kilowatts per charger. Not to mention if you have, say, 2 cars, but per charger is 19 kilowatts. That's a big deal. That's well more than all of this combined. And we're adding this stuff at scale to the grid right now. And I'll kind of show you what that looks like on the next slide. We have a project up in New York City, 550 chargers. And there's a funny little illustration there to show what that kind of looks like from a quantitative standpoint. It's a lot, and it's all for multifamily. And this is the trend we're seeing. 6 megawatts of demand these chargers put on the grid. 6 megawatts. To give you an idea of how that sort of plays into, well, what does everything else look like in New York City? A typical high-rise has around 2 megawatts of demand. So this is over 3 times the demand of the average high-rise in New York City, just the EV charging infrastructure. So the amount of energy that's being placed onto the grid related to charging vehicles is soon to become the largest load on the grid today. Right now, it's HVAC. Very soon, it's transitioning to electric vehicle charging. We'll go to the next slide. So why am I kind of telling you all this? Because, and we'll get to what the data has to do with this, is Well, customers who generally don't know a ton about EV charging, but they know they have to put the infrastructure in, they say, how do I not do that? Number one. And then how do I avoid any kind of peak demand charges, which can consume well over 100% of your bill, especially in New York and other areas of the country. How do I, not put the infrastructure in because it tends to be cost prohibitive and space prohibitive, and how do I avoid peak energy charges in my system? So we'll go to the next slide. So from a data perspective, charging directly from the infrastructure is critical because you can easily sort of aggregate and get feedback loops for everything. In other words, once you become part of the building infrastructure, you can then say, well, how much does the building have available real time? And with sort of instantaneous data, we can then say, okay, well, let's throttle up and down the charge rate to the vehicles depending on what we actually have available within the building. And so this avoids one sort of day one problem, which is how do I not put in, say, that 6 megawatts of infrastructure? Basically, what's in the green there, you can say, well, the building ebbs and flows. So if you can get real-time, accurate, instantaneous data, you can do these sort of things. And there's some nuances on why the accuracy and the timing of the data is important, because ultimately doing this, you're basically saying, hey, let's put more load onto the building than we actually have capacity for, which ultimately becomes a life safety problem, or could be. So you have to be able to guarantee that, be able to guarantee quick, calculated responses from the data. And the other advantage this kind of has is, the ability to do integrated demand response and peak curtailment and things like that to shave off those costs of peak demand. And so we're doing this in our own facility today, which you're all welcome to come out and check out. But, we don't have capacity for the chargers we've put in to our facility. So we do this today. We basically over-provision chargers and get real-time data, real-time calculation to, tell when we should throttle up and down the charge rate. We can go to the next slide to kind of show that. And this is where the data becomes really, really critical. And you can kind of see this happening here. This is, again, in our own facility. The sort of line on the top is the full billing load, and then the line on the bottom is our EV charging loads. And you can see how we curtail the EV charging loads real time as, generally speaking, our HVAC kicks on. That's what those kind of sharp spikes are there. And we'll curtail that load to keep it under 60 kilowatts, which is our setting right now. And this isn't much to look at from a complexity standpoint. This is a really simple thing. Okay, well, let's curtail peak demand and let's also not have to put in the infrastructure. But it's really the real-time accurate data calculations that go into being able to do this that you can best served at the infrastructure level. And even though those calculations are some complex, some simple, this has just the data calcs and the sort of data algorithms that we're using that enable us to save customers millions of dollars day one from lower infrastructure costs, if any infrastructure costs, and then millions day two, depending on the size, of course, to peak demand curtailment. So for us, data and the process of data processing and comparing that to a feedback loop from what is the building actually doing real time is really, really critical to ultimately save customers millions of dollars. So thank you.
Excellent, Ryan. Thank you so much, man. That was great. I've worked in and around EV charging infrastructure for a while, and I learned quite a bit more than I did. That's really cool technology. Thank you for sharing that with us.
Thank you.
Now we're going to kick it over to Keith Davis, president of REIG, to talk about deploying edgeware, acquiring, collecting, and delivering data. Keith, over to you, sir.
Okay, thank you all. Good afternoon. My name is Keith Davis, president of a little company here in Charlotte called Renewable Energy Integration Group. We shorten it REIG or RIG or however you want to say it for short. We are a small firm, 15 people that work in the Southeast and across the country with anything to do with solar data. So we do zero export, we do fiber, we do design, we do install. If it's solar data, we do it. And that's probably as easy a way to say what we do. Okay, next slide, please. So at the edge, I'm thinking about now out in the PV array. Remember, this is where I come from. What are some of the edge connected devices that we're so used to looking at and talking to? Well, first is the solar photovoltaic inverters. These are intelligent devices that convert the DC energy created by solar PV to AC, which can then be delivered to the grid. But each of those devices has a very strong computer built in to regulate that device, what it's doing, when it's doing it, how it's doing it. We make it a point to always, but always talk to them and ask them, what are you doing? And it replies to us, I'm doing this. In the far northeastern part of the state, the wind turbine industry is very much alive and well. They convert moving wind into clean energy with modern high efficient generators, turbines, if you would. We don't do a lot there, but we have seen that before. It is something that is has to be monitored and controlled. But then you think about the other things that are out there. We're looking at chicken litter, swine poop. There are so many different directions that renewable energy is going across the country, not just in eastern North Carolina. And so we try to keep our fingers on the pulse of any and all of that so we can be assured we are part of the solution. But coming back to the solar farm, let's look about the other smaller things that most people tend to forget. And that's first off is meteorological sensors. How fast is the wind? How much wind is blowing? What direction is the wind? How much sunshine is showing? What's the temperature of the modules? A host of different ideas that we have to measure. And when we put those into an equation, we can calculate what the grid should be receiving from the farm. And so when they start varying by more than a couple of percent, we start looking and say, what's wrong? We also have tracker controllers. These are the devices put out by third-party manufacturers that make sure that the single axis trackers are always tilted the correct direction during the day to follow from east to west and then stow flat overnight generally. And we talk to those. We make sure we can pull data from those to make sure we are getting the information we need from that. Irradiance, module temperature, wind speed are all very, very critical here at the trackers. We also look and talk to grid protection relays. So an SEL, say 751 relay, which monitors current and voltage. And when things get out of parameter, they will trip, opening a main breaker, signaling an alarm, setting off a problem for somebody to say, we need to do something about this. We're seeing this more and more on grid devices everywhere on the grid. Of course, metering is something very important too. Ryan's talking about that, but at the heart, there's a meter that tells you how much demand, how much delivery, how much generation I'm doing. So we always make sure we put in a high quality meter, depending on the customer's budget and how they want it. Then you think about protocol adapters that convert Spanish to English in this case, or Modbus to TCP, or serial over to fiber. We will put all of those things in to build a complete network. So when you think about it, we're really talking about the Internet of Things as sites grow larger and more complex. Next slide, please. So in our world, edgeware is any device, communications, infrastructure, or a simple enclosure designed to connect widely separated energy generation and related assets together with a common network. And so we have to build that common network. So many times it gets left out and they say, oh, we need fiber. Oh, we need radio. But early on, we need to make sure that we have everything we need to build that network with. An enclosure that houses all the switches and power supplies, UPSs. How about a communications infrastructure, something as optical fiber cable, a wireless Ethernet radio, or category 5 or better fast Ethernet cable? And did you know there are more than 20 different types of fiber? That's single mode, multi-mode. Is it direct buried? Is it riser rated? Is it, and you go on and on. And so making those decisions is an important part of the decision making into what is going on. We're also seeing now newer technology like low-Ra WAN, Zigbee wireless, and Bluetooth-enabled devices to communicate We're particularly seeing this with string inverters. Rather than running a Modbus cable from inverter 1 to inverter 32, they each have a low WAN radio or a Zigbee wireless net with it, which then collects the data and sends it on to the data collector. Every device has some type of built-in communications capability that is a component of the generating part, and it must be connected to the network to allow data from the device to be acquired. So that's acquiring that on EdgeWare. Next slide, please. Now that we've actually acquiring the data with the network in place and functional, then the data acquisition process can really take place. It's just a group of numbers until we start putting it in a format that makes sense. The asset collection information from itself is predetermined data structure often using an industrial protocol called Modbus. Modbus is an old language, first developed by Square D many years ago, but it still remains prevalent in the solar industry, whether it's plain Modbus or SMA has their own version, Schneider has their own version, but at heart, it's still a Modbus cable, which is a table of 16 bits or 32 bits, allowing us to collect that data and then pull it out. A central data logger, this is the device at the very heart, polls each device, asking for its information and asking for data from specific Modbus data registers. So they look for specific addresses within that device, and then whether it's 16 or 32 bits, signed, unsigned, long, short, doesn't matter. We just have to tell it what it is. The data logger polls that device on a very specific time frame, depending on how often the data is needed. Weather sensors, once a minute is usually fine. We don't need to know that the weather changes that quickly. Inverters, once every 10 seconds. And meters and relays is once per second, which is still an eternity to a utility engineer. They like to see things in sub-second data. And we can do that if you need to using the SCL software. Next slide. Oops. Next slide, please. There we go. So then we collect it. The data logger then collects the acquired data into a table. Typically, it's an Excel, CSV, comma-separated value sheet, or some variation that can be easily be manipulated by a third-party software or person. It's stored by device name, register name, data type, data value, and once per second is stored in a different table than 10 or 60-second data to keep them separate. You could actually have a table, one for meters and relays at 1 second, one for inverters at 10 seconds, and one for everything else at 60 seconds, and let all three of those report out. The larger the system, and that's a key component, the more data that is collected, but it's still only measured in kilobytes. We talk about megabytes and millibytes and gigabytes out in the field, and as a rule, that is not required. A 10-100 system usually will do whatever we want it to do for now. I'm not saying what the future may not bring. Next slide. So the data logger sits in an enclosure back up at the substation, the point of interconnection. It's connected to the internet with its own IP address and rules to push the data to a remote server through file transfer protocol or SQL or one of the other newer protocols that the internet has developed for us these days. This parses the data into blocks and individual values, and a user interface software on the server provides the graphs and images of the data. So we see real-time or near real-time graphs of meter operation. And once a minute, we see the irradiance change, the wind speed change, the wind direction change, the backup module temperature change. It makes it easy to visualize and understand by human because we're not number crunchers by heart. But as sites grow larger and the data collected exponentially increases, often artificial intelligence is employed to look for trends and anomalies indicating failures. We're seeing that now with North Carolina Electric Membership Corporation using another Cary, North Carolina company called SAS to use their SAS software to look for anomalies. And these anomalies are popped up much faster than a human being could find it. and they respond very quickly. And this provides system operators the ability to respond before the failure occurs, or if the failure does occur, it only occurs for a few brief moments before it's shut off. Next slide. So to wrap this up, the network is critical to the data acquisition process. And I say this is where so many people fall short. We go with the cheapest option. We find the cheapest software we can find. We find the cheapest fiber we can find. And we're not paying the attention to that we should, because the edgeware has to be coupled with the infrastructure structure, and it makes the network backbone. And without the backbone, we don't get data, and then everything breaks down. Then the data logger is the central device that acquires data. And Modbus is usually the most used communication protocol, but there are many, many others, and we have to be well versed in each of them. And once that's done, it collects the data to an easily managed format that gives it a consistent data block, and structures ensure accuracy after assembly, then delivers the data to servers running special user interface software that bring the data to life. Again, we are not number crunching people. They create charts and graphs that allow us an easy and fast to understand view of system performance, much as Ryan showed us just a minute ago. And that is next slide. And I'll turn it over to our host, and then he can turn it over to Chris.
Keith, thank you so much, man. I remember 20 years ago, I was still in college, and I did a session with a summer internship at a nuclear plant in South Texas. And I worked for about a week on the crew of guys that would go through the plant and take vibration readings on rotating equipment. And that was the old school way of doing data acquisition.
It
So it's
was
pretty amazing to see just in 20 years how far we've come, and the ability to collect data and act on data with speed. And so that's really interesting. I've got a couple questions for you already as I'm thinking about.
Okay, we'll answer them later then. Thank you, Sean.
Keith, thank you so much. Next, we're going to turn over to Chris Thomas. He's the Director of Operations at Ecoplexus to tell us a little bit about putting grid edge technology to use. Chris, over to you, sir.
Thank you, Sean. As Sean just mentioned, I'm the Director of Operations at Ecoplexus, which is a developer, owner, and operator of utility-scale solar plants globally. I've been in power generation for about 16 years. I've spent the past 6 years specifically in solar, and I currently oversee the teams that provide monitoring or remote operations, the plants we own and operate, as well as the performance engineering team, which focuses on deep dive analytics, modeling, and performance reporting of our operating portfolio. In order to perform those tasks, though, and ensure that we are operating within compliance of our interconnection agreements, O&M agreements and such, we deploy a network of integrated edge technologies, which Keith really just kind of laid out for you, and I'll kind of go over in from a sort of a different perspective, but much of the same. Next slide, please. So I'll focus mostly on our SCADA system here, and our SCADA means supervisor control and data acquisition. As it says there, right, that allows for real-time monitoring, remote operation of all of our equipment on site. We're able to trend all sorts of data, provide a lot of analysis and analytics, data exports and things like that. This is really a key driver of our performance. It helps us maximize our uptime, our production, and really maintain the systems that we have under management through a remote connection. And that remote connection consists of a number of things. We'll begin with the network communications. And as Keith mentioned, network communications is really really the backbone of this system. That's, our modem switches, our all sorts of devices that allow us to communicate from device to device, and then from device to the end user, which is typically our remote operations team, our monitoring team, and our performance engineering teams. But yeah, that is essentially, without that system, without a really solid network, as Keith mentioned, it makes that job very difficult. It makes it very difficult for us to stay within that sort of compliance. So really key, and I agree with what Keith mentioned earlier, that we should probably pay a little bit more attention to the networking side of things and ensure that we have a very strong network, especially as cybersecurity starts to become more of a concern. So secured porting, HTTPS porting, right, IP management, VPN tunneling, that sort of stuff. really starts to become important as we try to protect those networks as best as possible for the systems that we're operating. A big portion of what we do is data collection, and as the SCADA name suggests, right, there's a data acquisition there. Well, that data it comes in really two forms. There's real-time data that comes into our SCADA system, and there's historical data. And those are really used for different purposes. The real-time data is mostly for the real-time monitoring of the plants, the plant operations, things that are going on, real-time alarming, things like that that are suggesting that maybe a piece of equipment is malfunctioning or underperforming. That sort of information. And then the historical data is extremely useful for a lot of the deep analytics or some of the deep dives that we take to optimize performance of the plants, to adjust modeling, a host of different things that we do with that data. But essentially, you've got to have a good set of data loggers, data concentrators, industrial PC servers, and things there. To make sure that we can collect that data and be able to interrogate that data and provide a good amount of information to key stakeholders there. Another part of this our SCADA system is the HMI integration. Now, this is typically the screens that our operators are using to interact with different devices on site, whether that's inverters or trackers, relays, reclosers, and things like that on site in real time. Allows us to make adjustments on the fly, respond to changes on the grid, changes within the farm itself, and adjust settings and all sorts of stuff there. So it definitely provides that sort of visual representation of the operating plant, and then also allows us to be able to view some of our key performance indicators to make sure that we're operating the plant optimally. And then just a number, and Keith kind of mentioned all these devices that sort of make up that system, our relays, our inverters, tracker systems, all that. All of those things there allow us to communicate with the site, with the different equipment, and manage that performance of the site. And then respond to grid activity, emergency situations, and things of that nature. The biggest thing, though, and one of the things that's sort of an area of this operation that's growing quite a bit is the analytics portion of it, right? So our performance engineering team focuses quite a bit on the deep analytics. And when I say sort of deep analytics, I'm looking at things at the 1 minute level, sometimes even sub-minute level, depending on if we're looking at relays at the interconnection point and things like that. But they're essentially assessing the performance of the plant, trying to optimize the equipment settings, maximize our production of the plant, and things like that. Also allows us to diagnose all sorts of equipment failure, underperformances, and then provide that sort of feedback, long range sort of production and equipment issues and all sorts of stuff to folks like myself and other decision makers within the company. Next slide, please. And I'll say some of the challenges at this point right now are, I would say probably forecasting, sub-hourly modeling, sort of stuff. Cybersecurity is a big one, and predictive analytics. We hear that a lot these days. There's a lot of talk about AI and predictive analytics, machine learning, that sort of stuff. What does that really mean? How can we use that in our operations? And I think there's a lot of ongoing conversations about that right now in terms of what's the best way to sort of use that sort of technology. But right now it's for, we're focusing on, how do we improve the forecasting, sub-hourly modeling, that cybersecurity, as I mentioned, troubleshooting communications issues, which is a big, it's been a bulk of the time. We spend a great number of hours trying to troubleshoot communications issues. As you know, as we mentioned earlier, our network and communication devices make up sort of the backbone of the system. And so there's a lot of time spent making sure that the network is operating in a healthy manner and that we are addressing those communications issues that allow us to operate the equipment remotely that we need to ensure the performance of the plant. Next slide, please. And I guess, I'll hand it over to Gary at this point. Thank you.
Chris, thank you so much, man. That was a fantastic presentation, man. It brings two things up in my mind. One of our team members in Houston just messaged me saying that he got a notification he's going to have an electricity outage for the next hour. And so it happened immediately. I mean, their electricity went out and he got the notification via text 10 seconds later, as well as I'm sure that everyone affected in that area did. And so just the speed that everything happens nowadays is pretty amazing. And then the second thing that I'm reminded of is that same experience I had at the nuclear plant in South Texas. They said one of their key cybersecurity advantages is that their technology is from the 1980s and nothing's connected, and so they don't have to worry about it too much if they're not connected to anything. And so that's kind of the good and the bad of being connected and being in the know and having things automated. But fantastic presentation. Thank you so much, Chris.
Thanks, Sean.
Next, we're going to bring up Gary Ratcliffe. He's the VP of Market Development Innovation for Hitachi Energy, and he's going to tell us a little bit about a utilities perspective. Gary, over to you, sir.
Great. Thanks, Sean. So I do want to thank STIA Partners and the Energy team for hosting the webinar, and also E4 for organizing the event. I was looking forward to the participation and glad I was able to join. So just a quick introduction for me. I actually started in the utility and energy industry in 1979, so that's dating me a little bit, as a power engineer at Westinghouse, and then later worked for ABB, and then in 2020, joined Hitachi Energy. So today I'm working with customers and also company stakeholders on the energy transition, grid modernization, and the digital transformation with utilities. So I inserted this introductory slide just for a quick overview of Hitachi Energy and what we do. So we have about almost 40,000 employees. Our global headquarters, our global headquarters are on the campus, our global headquarters are in Zurich. Our North American headquarters are on the campus of the NC State University. So you can see that, again, number of employees, but I think what's important on this slide is just where we focus. We're the #1 provider of power equipment for industry and also utilities. We have 4 different businesses, transformers. You have factories here in North America, outside of Montreal, 2 in Virginia. We have our largest one in Jefferson City, Missouri. We also have another factory down in Mississippi. High voltage equipment, this is large power breakers, as well as gas insulated substation and other equipment. Our main factory in the US is outside of Pittsburgh, Pennsylvania. Grid integration, this business is primarily focused on the campus here, but high voltage DC, FACS, which is flexible AC transmission systems, substation, turnkey substation and engineering, and also high power EV charging. And in the business which is most relevant to today's discussion is our grid automation business, which has enterprise software, network control, software systems for grid operations, energy market systems for independent system operators, also market intelligence tools for tracking and monitoring generation resources, and also the cost structure. And then substation automation, utility communications, and grid edge solutions. And then at the bottom is the breakdown of the customers, and you can see our customer base is distributed between transport and infrastructure and industry, but also utilities, different product offerings that we have. And we're pretty equally split between EMEA, Europe, and the Americas in terms of market, but the US is our single largest business. Next slide, please. So this webinar, is focused on more grid edge and energy data and the tools to manage that data. So I just wanted to talk a little bit about, the distribution grid and some of the products and systems that we see being deployed at the edge of the grid and at the distribution level. For distribution systems, the core of the operations is the distribution control room, and this is sort of represented at the top center of this slide. Today, distribution grids are managed with ADMS systems, advanced distribution management software, that are connected to substations and smart field devices, including storage. So key functionality of these systems includes outage management, also managing voltages along distribution circuits, managing automated switching, in addition to having a network network model. So on the left side, just some of the drivers behind the need for active network management of the distribution grid. This is the reliability, resiliency, efficiency, sustainability. Across the bottom are some of the smart loads, smart devices for demand response and distributed energy resources, plus management, data management, and requiring or basically driving customer data and customer value. Then on the right side, you can see the different applications for asset performance and work in asset management. Next slide, please. So this is just a schematic which shows an advanced distribution management system. In the red, sort of in the center top middle, you can see the different applications of an ADMS system. As I mentioned, doing switch order preparation, different acronyms. FLISR is fault location, isolation, and service restoration. This involves automated switching, outage management, VoltVar control, which is voltage optimization along distribution circuits. UBLF is unbalanced load flow. That's using the network model and the load flow for analyzing the grid, and then also SCADA, supervisory control and data acquisition functionality. And the gray boxes on the upper right is where we get into the data management and the IT integration. So the customer information system provides physical location of customers, the meter ID, and also the electrical location, which is typically the distribution transformer. Enterprise and asset management basically enables management of materials and resources and crews. The geographic information system is important. It's the system of record for the network model. It provides equipment location as well as what connects the equipment together in terms of wires and conductors. We can then calculate impedance and then have a load flow, which really helps with driving simulation and determining performance and operation of the grid. And that's why I called an ADMS system a digital twin of the distribution grid. So the network model does multiple functions, as I mentioned, simulation, but also equally important is it can check the dispatch schedule of aggregated distributed energy resources to make sure the grid will be able to handle it. The utility or the distribution system operator is responsible for the integrity and performance of the distribution circuits when DERs are dispatched. Next slide, please. So this slide is more grid edge solutions, which could be part of the distribution circuit or could be behind a customer meter. For example, the utility can deploy a microgrid for reliability or resiliency purposes, use battery energy storage for capacity firming for renewables. It could operate this part of the grid either grid connected or in island mode. So the battery storage is frequently bundled with the microgrids. It can provide grid services when grid connected. When operating in an island mode, it can enable 100% renewable generation with grid forming inverter controls. Also, behind the meter, a commercial site may implement a microgrid with battery storage to manage peak demand, perhaps also provide capacity firming for on-site generation, and provide, basically enable greater utilization of renewable resources and also provide backup power. And then the bottom of the slide just shows, the DERs, the distributed energy resources, including the energy storage. In the center, you see the core grid edge control, which includes microgrid operations, SCADA, and automation and energy management. And in the top, advanced applications for analytics and energy optimization. Next slide, please. I wanted to include this slide on DERMS, which is Distributed Energy Resource Management. And there's a lot of information packed into this slide, but there's really four key components or key areas that where DERMS is used. So the first is registration of distributed energy resources for hosting and aggregation. Basically, this establishes also the ability to monitor the DERs to ensure availability, measure actual production, and validate the performance. Two is dispatch. It's basically dispatching control, monitoring of the distributed resources. Third part is the market settlements and transactions. DERMS is basically when you aggregate and dispatch, there's financial transactions involved. You need to be able to provide the settlement for that. And the fourth, and this is something that's critical from my perspective, is managing the grid when you have distributed energy resources. And as I mentioned, the utilities or the distribution system operators are responsible for the grid performance and actually can use the ADMS system to simulate a dispatch schedule in advance and make sure that the dispatch that the aggregators want to implement will actually be able to be scheduled and executed versus being curtailed, potentially curtailed. Next slide, please. So also when we talk about data, and this is, for distribution systems, this also extends also to the transmission grid for utilities. One of the challenges is utilities often have silos of data and lack of visibility across the organization. This is in part because you have different owners of different IT functions, such as the customer information system versus, the network control, which is part of operations and engineering. So what happens is, as a result of these silos, you can end up with multiple instances of data being repeated in multiple systems. Only a limited amount of data tends to be used for decision making. A lot of money is spent. Over 50% of the money on IT projects is spent for IT integration. A lot of the machine learning, the AI machine learning models never make it to production because the data isn't either reliable or something that can be used to obviously infer and make decisions. Costs go up. There's no trust in the data. This results in a little bit of a vicious cycle. So there's a lot of inefficiency when you have data silos and lack of visibility. Next slide, please. So there is some hope where we can look at re-architecting utility IT infrastructure to better manage the data. And in this particular slide, across the bottom, it just shows digitally enabled products that form the grid from generation to customer loads. And using IoT and connectivity, the data can be captured in a common data layer or data fabric that supports multiple applications hosted by a solution framework or platform, which could be typically cloud-based, either on-premise or hosted. Then these applications enable business solutions such as asset management or energy management, risk management, asset performance, etc. And what's shown with the coloring is, for example, if you look at transformer reliability, the peak shading shows the apps that drive this utility value stream. Could be geospatial visibility, could be sensors such as acoustic monitoring, could be asset prognostics, prescriptive analytics, could be AI, machine learning tools, could be time series data. But for an asset like a power transformer, utilities want to know its health or its condition of the asset and also its expected performance. So utilities need to know what is the risk also of the unit if it does fail in service. So how important is the unit? And those two factors really drive how you prioritize maintenance, how you make sure that you have the performance that you need for the utility operations. Then you can also pull in other components of the applications for risk involving reliability engines, the asset register, substation models, equipment loading, all of those factors that really drive towards knowing condition, knowing importance, and managing risk of operations. And this is done with a hosted platform accessing multiple sources of data. So final slide, just to wrap up. We have a data transformation opportunity at utilities. It's not just the energy transition and decarbonization, but it also impacts grid modernization, that reliability, resiliency, the efficiency, power quality, and security of the grid. So this just shows three strategic domains. The energy system automation, which really is strengthening the core IT systems. It's managing the increase in diversity of smart systems, particularly at grid edge, and also generation control. And this needs modularity. We need to make sure that the integration is easy and we have the ability to scale. Then you have energy infrastructure digitalization, really sharing data across the utility enterprise. Two key applications are asset performance management, which I just mentioned on the previous slide, to maximize customer lifecycle values and also efficiency and useful life of assets. And then the other is network control to provide end-to-end visibility and the optimization of reliability, risk, and performance for grid operations. And then the last one is the new energy ecosystem, expanding at grid edge so you can support increased electrification. We've talked about EV charging, sustainability pathways. We've talked about solar PV. So you have energy supply, both centralized and local, needs to be balanced with smart, controllable demand. And so we're seeing new markets emerging for energy management and optimization. Next slide. So this is my last slide. I only included this so you would have my email if anybody had any questions and didn't want to ask in the webinar. But so let's move on to the next slide, please. And I'll turn it back to Sean.
Barry, thanks. That's fantastic. I think the most striking thing about your presentation is how much research and development and innovation has been put into how Hitachi approaches grid management and the software related to managing that. There's so much stuff involved nowadays and interconnectedness between different nodes in the system and data that you need to acquire and think through and how to best optimize a grid and the distribution of energy. And so, I mean, for me, one of the things that really stood out was on the energy storage front. I mean, that's a huge burgeoning area. California is kind of leading the way in terms of energy storage and distribution of that energy. But it's something that's going to be an important topic of conversation for all grids in the U.S. over the next 5 to 10 years. Gary, thank you again. That was fantastic. We will be passing it off to Sebastian Gerber, who's Managing Director with SIA Partners, to tell us a little bit about grid intermittency. Seb, over to you, bud.
Cheers, Sean. I'll save everyone a presentation as SIA Partners. I think Sean and Shane have done a good job in introducing it. I'll just introduce myself. I'm Sebastian. I've been working in the energy and utilities field for about 15 years almost, and for the last, I'd say, good 5 years, I've been trying to help control room engineers and control rooms, like sort of introduce a bit more data science and artificial intelligence, machine learning techniques into their operations. So without necessarily going straight into various systems, etc. So what I want to talk about is give you sort of a real life example of on things that we've been doing here in Great Britain and mainly in Scotland, and see how that can work with effectively with the increase of renewable sources. If we can go on to the next slide, just to give you a bit of context, because I appreciate that obviously you are all guys based in Carolina, and so what's going on in GB. What we've seen is that there's been obviously a great increase of renewable energy sources over the last few years, with effectively installed capacity like increasing fivefold in the last 10 years. But what's effectively more striking, especially in GB, is that obviously that generation is mainly connected to distribution networks, right? So when you see generation connected to that transmission network, like pretty steady over the years, you have that penetration going down on the distribution grid. And now obviously distribution operators and transmission operators have different responsibilities, different level of maturities, and obviously different view of the system altogether. And currently in GB and on a specific part of Great Britain, you end up having entire regions that are now exporting back onto the transmission grid. That is something that was not really seen even 5 years ago. We had complete grid supply points completely exporting back. And we now see that you have over 20% of generation that is completely intermittent, completely asynchronous to the system, and therefore needs to be managed at a level that was not anticipated before. So if we go on to the next slide, in terms of what does it actually mean for the distribution network operators, it means a greater sense of uncertainty. It's like when before you had quite steady demand, you knew what people were going to do. Here in Great Britain, probably around 5 p.m, people would just turn on the kettle to get a cup of tea and all of this, right? It was fairly understood, fairly stable. Now you introduce a lot of uncertainty. Coming from those renewable energy sources, with weather conditions changing rapidly, increasing storm events or extreme events from climate change. So there is a great sense of uncertainty. Similarly, because of the fact that they are less synchronous generation, you increase the need for flexibility because of the volatility, and the balancing activities add distribution level and at very local level becomes now increases effectively the requirement for flexibility products. So those products are being developed and various mechanisms are currently underway, but obviously for the distribution operators that becomes a challenge. Also, one of the key things as well is that the generation that is being deployed on the distribution system is not necessarily always in light and scene of the distribution operators. You have people putting solar panel on their roofs without necessarily the network operator being fully capturing the information coming from that. You don't necessarily have control of teleoperations from all the networks that are connected to the grid. So therefore, the network operators have to manage effectively generation sources that they cannot control. So they have to anticipate what's coming up. And that creates more and more constraints effectively on the network. With that penetration, we see greater and greater risk of having congestion and constraint management from effectively like a supply point, like exporting back onto the grid. So what does it mean effectively for them, and how can we help them? So if we go on to the next slide, well, we've put together for a region in Scotland managed by Scottish Power Energy Network, which is effectively held by Iberdrola Group. So it's a large Spanish retailer. What we've developed for them is a full view, a modeling of their network with all of the generation assets connected to them, and try to understand effectively when the control room engineers actually look at a net load curve on their system that they see either at the substation level or even at the feeders of that substations. What is it actually made of? What is it made of? What is the share of that is effectively your true consumption at the end of the feeder, and what is effectively backed up by the generation connected to that feeder or connected at that substation? And by having this disaggregation, effectively, what we can do is then develop specific models for each generation asset on the grid, as well as demand models, which are probably more well established, I would say, based on historical data, to effectively understand what will be the position tomorrow of every single point of your network, every single node of your network, what will be the net flow tomorrow, and can the grid support it? So what turns out is that we collect all of those data that we have, like from the SCADA, from the generation assets, and we try to understand the share of each true demand, raw demand, if you like, and the backed up generation. And based on historical data, we're capable, and the weather data that was associated with it, the various explanatory variables based on calendar, weather, and others, we're capable of developing those models. And what we do is that every day, multiple times a day, we reevaluate those models against the new set of variables. So the new weather forecast that's coming through, the new a new shape or trend in demand, because we understand that there's been an EV infrastructure that's been connected, and all of that sort of backs up to understand what tomorrow the position of the network will be like. So if we move on to the next slide, what does it look in? I think I talked through this slide. I thought that you guys wanted to get rid of it, but anyway. So basically, what it means is that if you imagine that at a substation you have a net demand flow, so your transformer flows that you see, we try to sort of split out the true demand and the generation, and sort of model each of them separately to get to a position in the future. So we're looking at doing this effectively on a very short-term basis. So we're looking at near real time all the way to up to 5 days, which is probably like the sort of where the weather forecast actually loses its accuracy. And we try to do this like on every single point of the network, realistically. So if we can move on to the next slide to just see what it could look like. What it gives the operators is obviously various level of visibility, and being comfortable about what it means. So if you see those two charts on the left, the blue curve is effectively your net transformer flows. The orange at the top is your true demand, and the bottom is the generation part that is connected to it. So you get effectively down to the feeder level. So we're talking here about like almost that, I mean, to wherever we have monitoring systems on the ground. Obviously, you can see that with that blue shaped line, a control room engineer might struggle to actually understand what tomorrow will be like. If we now start disaggregating by actually understanding what is the true demand and quite stable over time and completely in line with what we know of demand should look like, and the generation, you can then anticipate what tomorrow will be like based on the various weather conditions. So in our case here, we had like a solar farm connected to a specific feeder, but that gives a good example of how we actually disaggregate that. And then we can do that at every single point of the network to provide a full network view of where your system is heading. And therefore, we actually assist control room engineers by providing that sort of high-level view directly in the control room 24/7, and each of those guys can access that through their individual computers as well. What it also allows you to do is understand how is my consumption actually backed up? Is it coming from the transmission grid, or is it actually coming from the generation that is connected to my own network? And that sort of is quite key to understand basically the share of those renewables, how you're actually going to be at risk of being affected by weather conditions, storm, etc., and how tomorrow will look like. So we can go from a very sort of top network view all the way down to your assets, and by using everything that my previous panelist actually talked about, which is how does the data get onto the system. Next slide, please. The next thing it allows you to do is obviously to understand where on your network are you likely to have constraints. So I appreciate the fact that those obviously are a bit small. I didn't realize they would turn up that small. But basically, from a high-level view of where your networks are, where the constraint of the network will look like, you can imagine to have like already alerting systems that will tell you precisely where. You can understand how much, when, where it's going to happen, and therefore put in place the best mitigation activities in order to manage those constraints. So we actually using this to support the decision making of the control room engineers. So whether there should be diverting loads by like switching. By diverting load from one substation to another, which could also be done sometimes as Gary mentioned through an ADMS automatically, but then you assist the decision here. You can imagine to activate some flexibility products. You can imagine to curtail some generation. All of those activities effectively can feed from the understanding of what tomorrow will look like. What it allows you to do as well is obviously to simulate the activity. So from the forecast that we are providing, we're capable of understanding obviously the impact of each individual of those generators, as well as each individual of the feeders. So if you suddenly have an outage tomorrow, we're capable of understanding clearly where that outage is how that outage is going to affect the rest of the network, and what you can do to mitigate the activities. So to finish, we try to actually bring together the data that is produced by the various asset generators, whether it is obviously like the EV infrastructure that we talked about, the solar panel that we talked about, and try and understand how this data actually can inform the control room engineers in the management of this intermittency on the network. And one point that I think is quite clear is how do you turn that data into a graphical user interface that actually makes sense? As our previous predecessors say, we're not data crunchers by nature, so having charts, having visual impact has been actually quite key in making sure that all of this data is assimilated in the right way, and the decision-making process can be, that the decisions that are being made are made with sound evidence. And I think that was sort of my last slide, I believe.